And so we move to the last speaker for today, which is Laure, which is presenting complex S-bearing molecules towards high mass star forming regions.
Thank you. First of all, I would like to thank the organizers for giving me the opportunity to present this work on the S-bearing molecules. I would like first to give you a brief overview and introduction to the high mass star formation. So high mass stars are the stars with a mass greater than 8 solar masses, and they are extremely important in our galaxy because this is the stars which will form supernovas, and they are also the stars who are capable of ionizing the surrounding gas. So here I give you a short sketch to explain how high mass stars are thought to be formed. And so first we have a massive dense core, which evolves into a hot molecular core. So what we call a hot molecular core is region where we have a temperature greater than 100 Kelvin. And this evolves into an H2 region, first an ultra-compact H2 region, and then an expanding H2 region. If we come back to the hot molecular core stage, is characterized by also a rich molecular emission. This is where we detected the first complex organic molecules, and we do not fully understand for now how we reach this molecular richness. So this is one of the questions. And it is important to study this warm-up phase because we observed now similarities between hot corinos and comets, but also some hot corinos and some hot cores. And the question of chemical heritage between the young stages of star formation and the comets and our solar system is still in place. So why do we want to study the hot core precursors, so the stages before the emergence of the hot cores? It's because the radiative feedback is not yet developed and we do not have a strong ionization yet. So we want to understand the physical properties of a gas during the emergence of a hot core and the early warm-up phase chemistry. And for this, we have large galactic plane surveys in our hands, and one of them is the Atlas Gal survey, which was done with APEX. It's a single dish, it's on the ALMA site, and we could observe different molecular clumps. And thanks to ALMA, we were able to zoom into these clumps. And here you see already a view with a 7-meter array and then a 12-meter array. And this ALMA view, we obtained it with SPARCS, which targeted 35 protostellar envelopes. And it revealed that 6 objects were singled down to 400 AU. So we targeted these objects with APEX because ALMA also revealed that we have a large molecular emission towards these objects and that they are hot core precursors. But the problem is that we had only 8 gigahertz of bandwidth with ALMA, and we needed more to study the full chemical composition of these objects to once again pinpoint the physical conditions and the chemical composition of these 6 sources. So what did we obtain with APEX? It's 206 gigahertz of bandwidth distributed between the 2 millimeter band and the 0.8 millimeter band. And we made sure to avoid artifacts and spikes to cover each frequency twice. This ensures us that we will be able to eliminate all these artifacts, and we are sure to be able to identify only molecular emission. So here I show you a spectra of the sources that we obtain, and you see that we can confirm, even on the large bandwidth, that we have a rich molecular emission. And if we look at these, a small chunk of the frequency coverage, we see that we have many differences between these sources. And so two of them are the S-bearing molecules and the comps. Here, I will talk only about the S-bearing molecules, but we will already highlight many of these differences. To explain you how we analyzed this data, I want to show you the methodology that we used. First, we performed the line identification of all the sources, of all the molecules, sorry. Then we performed line fitting of all the lines, and it gave us the line width and the line position for each transition of all the molecules. And finally, we built up a rotational diagram. So the rotational diagram would describe the population level in each transition, and we can extrapolate to obtain the total column density of the molecule and its rotational temperature. From there, we went to the LTE modeling to have to obtain the size and the temperature and the column density of each molecule. Of course, when we have only single-dish data, we needed to assume the size of the emission, and this triggered an iterative process to have a good estimation of the size. When we have ALMA data, we do not have this problem, and we can calculate the size of the emission and put it in our model directly. And finally, we have this, we obtained the physical parameters for all the molecules, and for, in particular for the S-bearing molecules, and we obtained the line widths, the column densities, the temperatures, and the sizes. And with this, we can go on the S-bearing molecules. So to give you a brief context and why the S-bearing molecules were an important part of this study, is I would like to explain the problem of a missing sulfur reservoir. So the sulfur reservoir is not yet known in the galactic plane. We have leads, and H2S and SO2 were tentatively detected on the grains, but no sure detection about this. Another reservoir which might be the S-bearing reservoir is OCS, and these three molecules are important molecules in the S-bearing chemistry. But the observation, so why are we looking for this reservoir, is because we have a depletion of 0.01% towards the hot cores, and this is extremely low. And we also have, and we do not know yet where we can find this missing sulfur. And finally, just to give you an overview of the typical abundances of S-bearing molecules in high mass protostars, is 10 to the power of -9. So the S-bearing molecules are also presenting an interesting chemistry. We have new detections coming up in the last few years. And for example, here, HC3S+. So now we are really trying to understand where this, how is evolving the sulfur chemistry, and how can we understand and model it. So in here, I give you abundances towards one of our objects and one towards one of our hot core precursor, and we see that in this object we have abundances of 10 to the -8 or 10 to the -7, even for some molecules. This is extremely rich. This is 1 to 2 orders of magnitude than higher than what we observe towards typical high mass protostars. So the question is, do we have a shock chemistry? Is it coming from the outflow? Unfortunately, for now, we don't know yet because we do not have the sufficient high angular resolution data. However, what we know is that we have different chemistry between the cold and hot envelope. So we could, thanks to our method, we could distinguish between the cold emission, the emission from the cold component and the envelope, and the emission from the hot component of the envelope. And we see that we have a large diversity, and we detect many ions in the cold envelope, which suggests that we have evolved chemistry towards the cold envelope, while what is happening in the hot envelope is completely different. We see that we have only few species detected, and also we see that while H2S is dominant in the cold envelope, it's not in the hot envelope. So it really suggests different chemistries. And we wanted to investigate this into more details. This is why we went into, we looked at the S-bearing molecules into all our sources. And here you can see the 6 different sources, the cold and hot envelope for each source. And you see that we still have a large diversity of S-bearing molecules in the cold envelope, while the hot envelope, it still has only few detections. But you can see that we detect the complex organic molecule CH3SH in most of the sources, and it's even in the coldest sources, for example, this one, where we do not have a hot envelope. We do not detect the S-bearing molecules in the hot envelope. We still have CH3SH. So the different contributions of the S-bearing molecules tells us that the complexity of the S-bearing molecules is there from the start of the high mass star formation. And so now I would like to show you some results that we obtained when we compared our S-bearing molecules with the different models and with the
3 minutes.
Yeah, thank you. With the chemical parameters, some chemical parameters. So the gas temperature of CH3SH is lower than the desorption temperature. So here you can see the desorption temperature calculated by chemists, and you see that for most of the sources, we detect lower temperatures. I put here a comparison with methanol, and to show you that in the cold envelope, methanol is below the desorption temperature, and so it dissolves from the grains through non-thermal processes, while in the hot envelope, it's dissolving through thermal processes. So CH3SH is behaving is behaving more like the methanol in the cold envelope. And when we look at when we look at the results of CH3SH in the chemical models, we see that the chemical models are over-reproducing the abundances relative to H2. However, which suggests that CH3SH is dissolving, might be dissolving through non-thermal processes, or that CH3SH is formed in the gas phase and not on the grains. Another point that another comparison that we made is that CH3SH with methanol. And these ratios are similar to what the models are saying. So it suggests that the chemistry is at least the link between the two molecules is identical to what the models are predicting. So all of this was done with single-dish data, and we could see that we are lacking the presence of high angular resolution studies where we can obtain the physical parameters in several points. And this is why we have the ALMA view. And there is this project, MAYA2023. You already had some presentations about these projects, but it targeted many regions in different evolutionary stages. And we obtained the view of different S-bearing molecules. So here I'm presenting only H2CS and CH3SH, but you can see that H2CS is extended and it's the emission is along the outflow, at least one of the lobes of the outflow. But CH3SH is mainly detected towards the hot cores. So the next steps of this study will be to understand how we can have CH3SH in the young stages and how it can desorb, while in most of the hot cores, it's detected towards the central positions and where we see all the overcomes. So this takes me to my conclusion. So we had, thanks to ALMA, we could identify some hot core precursors, and we could see that the S-bearing chemistry was already there and was extremely evolved in the young stages. We see that now we have a source G328 where the S-bearing chemistry is extremely developed, and this is a good target to understand the chemistry of sulfurated species. And CH3SH is a molecule which is important because it's a complex molecule, and it's found in the cold gas, even if it is not where we should expect it according to the models. And finally, ALMA is revealing the distribution of these molecules, and it will help us to understand this chemistry and to better constrain the models. Thank you.
Thank you, Laure, for the nice talk. Other question? Okay, there are two questions. Abhijit?
Yeah, hi, thank you for the great talk. I was wondering, towards your last point, I think your selection of these sources was that the ionization procedure has not started yet for these cores. So is the conclusion that because of that, the CH3SH can still survive towards the center of the core, or am I understanding it wrong?
No, so the first sources that we selected were expected to be young, and the chemistry in its young stages and not too evolved, that the central postal star didn't warm up its environment and didn't trigger another chemistry. So what we see is that CH3SH is already there. This is the surprising point. We expected that it shouldn't be there, or not in such large quantities, but it's already there. So this is the surprising point. So now with ALMA, we want to understand how it evolves and how it gets into hot molecular core.
Thank you.
Another question, Sebastian?
Yes, thank you, Laure, for the very interesting talk. You show a plot of different sources with a different composition of that one. I was wondering if you could order the sources in like a kind of evolutionary track, or could you use the species to decide to get an age or to estimate the?
So sorry, yeah, I forgot to indicate it and to say it. This is already into an evolutionary track. So this is the youngest source, and it goes down towards the most evolved source. So the other molecules tells us that the last source is not yet a hot core, because we do not have the physical parameters for the hot core, but its molecular emission is extremely close. So here we see that when we we see that SO is taking more importance in the S-bearing molecules, while CS is being reduced. So this is still in. We still need to make a detailed comparison with the models, because we do not have models dedicated to these sources. So this is, for now, still a work in progress, because we need the help from chemists and people doing models, chemical models.
So which tracer, what did you use to get the age, the sources?
We used the temperature, the gas temperature. So we do not have the age. We have a sequence between all our sources. We have the age only for one source, which is G328, and it's thought to be 10 to the power of 4 years.
So do you have some hope that the sulfur-bearing species can be used as clocks, or?
So we made some comparisons, and for now, we see that these sources are younger than the hot cores. This is what the S-bearing molecules are telling us. However, we cannot distinguish between all these sources with the S-bearing molecules. This is not this chemical clock is not precise enough.
Thank you.
Yeah.
And there are more questions? If not, thank you, Laura, again, and we stop here.